Hello, myself Professor Harish Mangade from Department of Electrical Engineering, SND College of Engineering and Research Center, EVLA. I welcome you in a lecture series of Basic Electrical Engineering of first year engineering course. We are discussing a single phase AC circuits. We are already discussed what is single phase AC circuits, what is alternating currents, what is alternating voltage, what are the different terminologies related to AC fundamentals that we have already discussed. Now let us today lecture will discuss about the AC through pure resistance. When we will pass a alternating current, alternating voltage will apply through pure resistive network or through pure resistance. In that time, what will be the nature of current and voltage that we will see in this lecture. So here, this pure resistance is here, and across it, the voltage, RMS voltage, voltage is applied. That is V is equal to Vm sine of omega t. So now before that, what is a pure resistance? A network or a circuit which consists of pure resistance in ohms, that is known as a pure resistance. Means there is no inductive and capacitive components in that circuit. So such a circuit is known as a pure resistive circuit. Now consider here a resistive simple circuit consisting of a pure resistance R ohms connected across this voltage source, and the voltage given as V is equal to Vm sine of omega t, where V is the instantaneous value of this alternate voltage, while Vm is the maximum amplitude, voltage amplitude of the oscillating potential difference. Omega is the angular frequency of the voltage applied. Now, an alternating current I will flow through this resistance due to this voltage source, and which will develop a potential drop across resistance R. So whenever we apply this voltage, that time obviously due to this applied voltage, a certain current will flow through this circuit. And this current flowing through this circuit will develop a certain potential drop across this resistance. And let us say the potential drop across this resistance is VR, that is equal to IR. So here the potential drop across this resistance V is equal to IR. So that much drop will be there across this resistance due to the application of this voltage and flowing of the current through that resistance. Now, according to the Kirchhoff's law, okay, loop analysis, to our voltage law, the algebraic sum of the EMFs of the voltage encountered in a particular loop is always zero. So that is, we apply here for this circuit to Kirchhoff's voltage law. So the summation of this and summation of this applied voltage and voltage drop across R resistance IR, it is always zero. Means we can write that IR is equal to Vm sine of omega t. So I is equal to, I can write Vm upon R sine of omega t. So this Vm upon R is nothing but Vm is the maximum value of the voltage, that is the amplitude. So it is Vm upon R. According to Ohm's law, it is Im. So I can write this equation, I is equal to Im sine of omega t. So here Im is equal to Vm upon R, that is the current amplitude. Okay, now from equation 1 and 3. From equation 1 and 3, this is my equation 1, V is equal to Vm sine of omega t, and third equation is Im sine of omega t. If we compare these two equations, then we will find that the current and voltage reach their maximum value, Vm and current, both will reaches their maximum value at the same instant of time. Also, their minimum value, that is zero, they also will reach at the same instant of time. So hence, I can say that current and voltages are in phase with each other. So here I can conclude that whenever alternative voltage is applied or AC is applied to pure resistance, that time the voltage and the current are in phase with each other. Okay, so the current and voltages are in phase with each other. So you observe this waveform for current and voltage. So this is the waveform for voltage. Okay, this is the waveform for current. So here the maximum value Im for current, here the maximum value Vm for voltage, and that are reaches at simultaneously. Similarly, zero value here also zero value for both the waveform, they are reaches at simultaneously at a same instant of time, and hence I can say that they are in phase with each other. Now the sum of the instantaneous currents. Now what we have to find? We have to find the power, right? In a pure resistive circuit where a voltage is applied, AC voltage is applied. So now we know that the sum of the instantaneous currents values over one complete cycle is zero. It is average value for a complete cycle is zero that we have already defined. So the average value for a current over one cycle of AC is zero, but we always find the average value for a complete cycle, not for a complete cycle, but we find always for a half cycle. Now, but though the average value for a complete cycle is zero, but the sum of the squares of all the currents for one complete cycle is not zero. So square of I square is always zero. Sorry, is always positive. So since I square is always a positive, irrespective of whether I is positive or negative, so the Joule heating and dissipation of electrical energy takes place when an AC current passes through a resistance. So obviously the utilization of that energy will be there, and it is in the form of the heat energy to the resistor. So the instantaneous power dissipated in resistor is given by P is equal to I square R. So the power, instantaneous power at any instant of time, it is P is equal to I square R. Now the I we know what is I is nothing but Im sine of omega t. So it's square, it becomes Im sine square, Im square sine square omega t. Okay, Im square sine square omega t into R. So it becomes Im square R sine square omega t. Now the average power over complete cycle of AC is P average is equal to I square R and is equal to Im square R sine square omega t. So since Im square and R are constant, both are constant, so I can write the P average is equal to Im square R sine square omega t. But the sine square omega t is 1 minus cos of 2 omega t upon 2. So I can write as 1 upon 2 minus cos of 2 omega t upon 2. So the average power, it can be divided into two components as Vm upon 2 minus Vm upon 2 cos of 2 omega t, means the two components are constant power component is there and fluctuating component is there, and the cos of omega t over a complete cycle is always zero. Cos of omega t for a complete cycle is always zero. Hence, and sin square omega t is 1/2. So P average I will get as Im square R upon 2. The same amount of DC power P is equal to I square will also flow through that circuit, and that will dissipate the energy in power as I square R, and if the current equal to I RMS or I flows through the resistor R, then P is equal to I square RMS, I RMS square into R. So, but P is equal to P. So, what P average is equal to P. So that you can compare this two equation, and I will get 5 and 6. I will get I is equal to I RMS square R is equal to Im square R upon 2. So I RMS square is equal to Im square upon 2. So I is equal to I RMS is equal to Im upon root 2, and that is equal to 0.707 Im. So similarly, in case of voltage, we will get the V is equal to V RMS is equal to Vm upon root 2 or is equal to 0.707 Vm. So the average value of the power waveform of the voltage and current, and the power we can plot also. So this is all about the power dissipated in your resistive circuit, and also the nature of the current and the voltage in the pure resistive circuit. So thank you. Next lecture we'll see the AC through pure inductance and AC through pure capacitance.